This is a wall of defenders standing in front of the goal. If you shoot directly from the front of the wall, the ball will hit the wall and bounce away. So you try to kick the ball high to go over the wall. Suppose the ball's initial speed is 8 mph. As it flies toward the goal, the ball pushes the air in front, creating laminar flow around it. Because the air can't fill the space behind quickly enough, a low-pressure area forms behind the ball. It's like a parachute dragging it back. That's pressure drag. This drag gradually reduces the ball's speed. Finally, under gravity, the ball follows a nearly symmetric parabola. It clears the wall, but because it's too slow, its descent is gentle and the goalkeeper easily catches it. So you try to kick harder. This time, you give the ball an initial speed of 15 mph. Using the drag formula, drag is proportional to the square of speed. So at 15 mph, the drag is about 3.5 times greater than at 8 mph. The ball's speed drops noticeably during flight, but because it started faster, it still travels much farther than at 8 meters per second. Its trajectory is a stretched, asymmetric parabola. The ball clears the wall at high speed, but then flies straight past the goal line, still no goal. Then you have a clever idea. What if, right after the ball passes the wall, you could suddenly increase the air resistance so that its horizontal speed drops sharply and gravity pulls it down quickly? That would allow it to drop before the goalkeeper can react. But you can't use a hairdryer on the pitch to increase drag. So you think back to the drag formula. Drag half by drag coefficient by air density by cross-sectional area by speed per. Air density and the ball's cross-sectional area stay the same, so only two variables matter, speed and the drag coefficient. But what exactly is the drag coefficient? From your two attempts at different speeds, you know that behind the ball there's a region of laminar flow. Laminar flow moves in smooth layers over the surface, but it separates easily from the ball, leaving a large low-pressure zone behind, like a parachute. The size of this parachute is what the drag coefficient represents. With laminar flow, the low-pressure zone is largest, so the drag coefficient is about 0.5. To shrink that low-pressure zone, you need the air to stick to the ball and not separate too soon. Then the low-pressure zone and the parachute get smaller. That's turbulent flow. With turbulent flow, the low-pressure zone is smaller and the drag coefficient drops to about 0.2. Now you reach a conclusion. If you can make the airflow over the ball switch from turbulent back to laminar, the low-pressure zone and parachute will suddenly expand, and the drag coefficient will jump from 0.2 to 0.5. The increased drag will rapidly kill the ball's horizontal speed, and it will drop sharply. You learn from fluid dynamics experiments that when the ball's speed exceeds 25 meters per second, the airflow over it changes from laminar to turbulent. So you put all your strength into a kick, launching the ball at 30 mph. During the first half of its flight, the ball is in turbulent flow, with a drag coefficient of 0.2. The drag seems small, but drag is proportional to the square of speed. Double the speed, quadruple the drag. Even with the drag coefficient cut in half, the actual drag is still 1.6 times greater than for the 15 meters per second laminar ball. This huge drag powerfully consumes the ball's horizontal speed in a very short time. That's the strong braking effect. When the ball reaches the area above the wall, its speed has dropped below 25 meters per second. The flow suddenly switches from turbulent back to laminar. The low-pressure zone expands to its maximum, and the drag coefficient jumps to 0.5. Now, with the braking effect added, the ball's horizontal speed drops to near zero within 0.5 seconds. At that moment, gravity takes back control of the ball's motion and makes it dive down in a strange, sharp trajectory. Finally, the ball scores. Congratulations, you have just discovered the drag crisis in fluid dynamics and successfully kicked a world-shaking knuckleball. In world football, the best knuckleball specialists often have incredible leg power. The initial speed of their free kicks often exceeds 30 mph, sometimes reaching over 35 mph. During matches, you'll often see them carefully adjusting the ball with their hands, turning the harder valve area toward their foot. This helps them strike more cleanly and gives the ball a higher initial speed. Truly, power creates miracles. Now you've mastered most of the core techniques of the knuckleball. So it's time to step onto the pitch and compete with the best in the world.